Have you ever thought about logic as an architecture? I mean, really thought about it. That the kind of rigorous, clear thinking we all strive for is actually built on a foundation. One with its own blueprints, its own set of tools, and even its own laws of physics. Today, we're not just looking at some abstract math. Nope. We're exploring the very structure of reasoning itself, all through the lens of operations on sets. So, let's start where any good project does, with the blueprint.
You know, every great structure has to start with a plan, right? A defined space. Well, in set theory, this is what we call our universal set, or U. Just think of it as the boundary for our entire project. It's got every single element we could possibly care about for whatever problem we're tackling. And inside this universe, we've got our specific collections, our sets, which we're calling A and B here. This is our canvas.
Okay, so an architect is absolutely nothing without their tools. To actually build with logic, we need to assemble our toolkit. And it all comes down to 4 fundamental operations that let us combine, compare, and really just manipulate our sets in some incredibly powerful ways. Our first tool is the union, and its keyword is OR. Super simple. An element gets included if it's in set A, or if it's in set B, or if it's in both. It's all about inclusion. It's expansive, and it creates a brand new set that has everything from the originals, just without any duplicates. Next up, we've got the intersection. So if union was all about expansion, intersection is all about precision. Its keyword is AND. An element is only included if it's in set A, and at the same time, it's also in set B. And what I love about this slide is how that Venn diagram just perfectly isolates that one little overlapping area. It's the common ground, the only thing they share. Our third tool is the complement, and it's powered by NOT. This is how we define things by what they aren't, and it actually comes in 2 main flavors. The absolute complement is everything out there in the whole universe that is not in A. But the relative complement, or set difference, is way more specific. It's everything that's in A but not in B. It's a real precision tool for exclusion. And finally, our fourth tool, the symmetric difference. Now this is the logic of exclusive OR, or XOR. An element gets included if it's in A or in B, but, and this is the whole key, not in both. The visual here just makes so much sense. You take the whole union of the 2 sets, and then you just carve out that shared intersection in the middle. Think of it like this: finding people who like either cats or dogs, but specifically excluding the ones who like both.
So here they are, our 4 foundational tools all on one map. We've got union for OR, intersection for AND, complement for NOT, and symmetric difference for XOR. These are the fundamental verbs we're going to use to build all of our logical statements.
All right, so we have our toolkit. But you can't just start building without understanding the rules, right? You need to know the physics of how your materials actually interact. And that's where these algebraic properties come in. They govern exactly how our operations work together.
These rules are what give our logic its reliable structure. It's why it works. First up, the commutative property just means order doesn't matter for unions and intersections. A union B is the exact same thing as B union A. Easy. Next, the associative property means that grouping doesn't matter when you're using the same operation. And finally, idempotent, that's a fancy word for a simple idea. Combining a set with itself doesn't change it. A union A is just A. Together, these laws make everything predictable and sound.
Now this should give you some flashbacks to math class, but in a good way. Remember how you can distribute multiplication over addition? Well, in set theory, you can do the same thing. You can distribute an intersection across a union, or a union across an intersection. The arrows on the slide show it perfectly. It's a way to break down a really complex expression into simpler, much more manageable chunks. Okay, De Morgan's laws are an absolutely fantastic shortcut for logical inversion. It's like a magic trick. If you want to find the complement of an entire union, the rule is simple. You break the bar over the top, give the complement to each set on its own, and then you flip the symbol from a union to an intersection. Now, why is this so powerful? Well, if you're doing any programming or database queries, simplifying a complex NOT condition like this can make your code way cleaner and more efficient. It's a key to really elegant problem solving.
So, we can operate on sets now, and we get the rules. But what about measurement? How do we figure out the size of these logical structures we're building? And more importantly, how can we do it without making simple but totally critical errors?
First, let's just get the terminology straight. The size of a set is called its cardinality. It's really just a precise way of saying the number of distinct elements inside that set. Simple enough, right? But this is where a really subtle problem can sneak in. Here it is. This is the trap.
If we want to find the size, the cardinality, of the union of A and B, our first instinct is probably just to add the size of A to the size of B. But just look at that diagram on the right. If those sets overlap at all, we've just counted every single element in that intersection twice. Our measurement is completely wrong.
So, to correct this error, we use this really elegant idea called the inclusion-exclusion principle. To get the true size of the union, you add the sizes of the individual sets, and then you just subtract the size of their intersection. That's it. It gets rid of the double count and gives you the exact answer every single time.
Now, what's truly powerful about this principle is that it scales up beautifully. Check this out. For 3 sets, the pattern just continues. First, you add the sizes of the individual sets. Then you subtract the sizes of all the two-way overlaps. But wait, doing that actually removes the very center too many times, so you have to add back the size of that central 3-way intersection. It's this careful process of including and excluding, adding and removing layers to get a perfectly precise measurement.
So let's just step back for a second and look at the complete toolkit we've managed to assemble here. We've gone all the way from basic tools to some pretty complex measurements, and it's all part of this grand architecture of logic.
We've learned to operate, manipulating our sets with those 4 core tools. We've learned to regulate these operations with the fundamental algebraic laws that give them a predictable, reliable structure. And finally, we've learned to calculate with precision, measuring our sets without any errors using the inclusion-exclusion principle. Operate, regulate, and calculate. These are the core skills of the logical architect.
You see, these concepts are so much more than just math. They are a universal toolkit for structuring information, for analyzing arguments, for searching databases, and for solving complex problems in pretty much any field you can imagine. You now have the blueprint for the architecture of logic. The only question left is, what are you going to build with it?